Hey guys, here we are doing our first recording for Math 70. All right. Uh, I hope the homework is going well, etc., etc. But I think what I'll do right now is just jump into 9.4 so that we can get that homework started. Okay? Don't mind my voice, it's getting a little scratchy from what I've been doing, but just so glad that we're able to use this technology so that we can study this together. This section pretty much, I know it starts off saying exponential growth model, and they do talk about this particular relationship. And of course, what it's saying in words, if we were to write this, is dp dt is saying the rate, the rate of population growth is directly proportional to current population. I think we've seen this before, and you end up going the rate at which it is changing with respect to time, you do a proportion on it. So it's k times p. I'm sorry if I don't remember if we've solved this before, but it is separable. You simply go 1 over p dp is equal to k dt. Integrating, got natural log of the population is, let's see, it's kt plus c. Therefore, taking e of both sides, you get that e to the kt plus c, which is e to the kt, remember, times some sort of constant, whatever it might be. And that's where you get this formula. Well, this particular section, they start that way, but then they go, that's not realistic, because what really happens in life is that you've got a population axis and you've got the time axis, and your population will start somewhere with some sort of initial population. Maybe it's up high, maybe it's down low, but it's going to add this added constraint, which is realistic, where there is like a max population, maybe sustainable. And we'll call that M. So what happens is typically we have a low population that is going to grow exponentially, but then it'll taper off and approach that max. Or you're overpopulated and some things happen and it decreases exponentially towards that limit. Okay. So what they want is that if the population is bigger than the max sustainable population, we want a negative rate of change. If it is below, we want it to be positive. But as either one of them approach the maximum carrying capacity, then you want the population rate of change to rate of growth to change as you get closer and closer. So to reflect that, check this out. That's the new model. It supplants this one. This is the so-called logistic model right there. And look how it's constructed. Sorry. I've got that's your proportion constant. There's your population, 1 minus p over m. Now what happens? If p is bigger than m, this is a number that's bigger than 1. If p is bigger than m, then you've got 1 minus something bigger is negative, and there you go. You've got a negative growth rate. What happens if it's less? Well, if it's less, it's going to be p is less than m. It's going to be positive, but you'll notice that if p is really, really small, then the one up here is good enough to predict, because it's going to curve upward. But as p gets closer and closer and closer to m, this gets closer and closer to 1, and the rate of change gets closer and closer. So as p approaches m, the rate approaches 0, the rate of growth of the population. Now it's a model. This is not really what happens, but it's a model. Anyway, it's an interesting model, and let's take a peek at this guy. dp dt is equal to kp and then 1 minus p over m. I might shorten, that is to say, not do the complete development of the model and then just give it to you and show you how to do the problems. But it's interesting to see that this guy can be done using our techniques of solving differential equations. Again, this guy's separable, just like the previous one. He separates, and believe it or not, you can write it out as, there we go with that A again. I don't know what's going on. Okay, 1 over P paren 1 minus P over M dP is equal to KT. Okay? This one is, the point here is we're supposed to integrate that, and I'll do the right hand side, you do the left, as I like to joke around. But the one on the left is a mess, right? We can do stuff to it. The thing that might be a good idea is to hit it with an M and hit this guy with an M, and that'll kind of clear things up in there. So let's take a look at what it looks like now if we do that. We've got integral of M over P paren M minus P dP. And what does that remind you of? I'll integrate this while we're at it. Oops, that was a K dt, sorry. KT plus the all-important C. What does this integral remind you of? What kind of technique do you think would be a good one for that? Well, I think it's a by parts. No, not by parts. Partial fraction, parts of fractions, partial fraction decomposition. So we would say that this side could be like, oh, I don't know. How about A over P plus maybe B over, believe it or not, M minus P dP. And it's a matter of finding those, the A and the B. You'd start off going like for instance, M, when you clear fractions, is equal to A times M minus P, and then plus B times P. And I won't bore you with the details, you know, let P equal M, let P equal 0. And you're going to find that A and B both equal 1. So a little work I'll cut out of that one. So we're looking at integral of 1 over P plus 1 over M minus P dP is this. Integrating natural log of the population. This is actually a small little U substitution. Let U equal M minus P. So that means du is minus dP. And the result of that is that you get a negative ln absolute, because I don't know if P is bigger or smaller than M minus P equals KT plus C. Okay. You can use oh, I'm running out of space, so I have to end. So you can use properties of natural log, P over M minus P. Absolute value around that is KT plus C. You can go E to both sides, etc. Okay. What you end up with is the formula, and I'm going to go the way he does it in the book. This is on page 614. It says the following. Here's your formula for this. For the logistic equation. You know what? I'm going to bring it down to the next page. So the formula is P, and I write P of T to be clear, is M, what's M stand for? Over 1 plus, and then he uses a letter A, but I'm going to throw the whole thing in there. I'm just going to go M minus P0 over P0 e to the negative KT. That's what it looks like. Okay, that's the one we're going to use. And so what are these guys? Well, we know what P is. P is population. What's M? Remember? It's max, pop, sustainable. What's P0? I think you know. Initial pop. Population. And K is a growth constant, big deal. And then it's, you know, let's write it down. K is growth, or could be decay if you're losing population, constant. And of course, T is time. It could be in years typically, but it could be other things as well. So I have on the docket to do a couple of problems together, and that'll be it for today's lecture on this. We're going to take a look at problem 6 on page 618. Okay, What it's saying here is suppose this. Suppose dp dt, and he gives us like 0.4p minus 0.001 p squared, and it also says p of 0 is 50. Okay. Well, that's not what I'm used to seeing. What I saw previously when we were developing this, more or less, was dp dt was equal to kp 1 minus p over m, like so. So the trick, and I do call it a trick by Stewart, is, hey, it's the logistic equation. He's saying here in the problem, suppose a population satisfies this where t is measured in years. So t is years. Okay, I'll write that down. How do you make, I mean, is this the same? It's not written the same way. What do we got to do? Write it the same way. Okay, to do that, for this equation here, factor out 0.4p. That'll give you 1. And if you then basically, when you're doing that, you've got a negative 0.001 divided by 0.4, and then there's a p there, and that's your new look for dp dt. How does that measure up? Well, the first thing I notice is that this k is this 0.4. So I'm going to write that down for this problem. K is equal to 0.4. And if I were to clean this up, I'd be able to figure out more stuff as well. Well, when you clean that up, you get this. dp dt is 0.4p 1 minus, and it turns out that that is p. That's like saying 1 over 400, so it's p over 400. What you're supposed to do on this problem is compare this guy, which started out this way, but we turned it into looking like this differential equation. And you're supposed to be able to go, oh, okay, now I see that this 0.4 is k, and I see that this 400 underneath here is m, so m is 400. Okay. They have a question. Part A is saying, what's the carrying capacity? That's m. The carrying capacity is m. So the carrying capacity equals m is equal to 400. Just from, basically this is a study of the structure of not only just the equation to use over here on the right, but also its differential equation. Okay, so we found that. Part B is saying, what is p prime of 0? B, what is p prime of 0 equal to? Okay, well, p prime is this, dp dt is equal to this formula, 0.4p, 1 minus p over 400. I could tell you what it is if I knew what p was. Dang it, what is p? This 0 that you're plugging in is actually t is equal to 0 because it's a function of time. Way up here, here's your formula. It's a function of time. The only live wire is that t right there in the exponent of e. So it's a function of time. So I know that 0 is t. Oh, wait a second. What have we done in the past? Well, we can build a table. What we have is here's t and here's p. Okay, fine. When in the problem, they stated p of 0 is 50. So 0 gives you 50. You know what? That's p0. That's our initial number. So what happens is you take this guy as an ordered pair and you go, you want the derivative? I'll give you the derivative. It looks like I have to plug in the p coordinate of the initial point on the graph. And we do. That's how you do it. So p prime of 0 is 0.4 times 50, and then 1 minus 50 over 400. Okay, take a pause there and study that. What I'm saying is, and what the book wants us to learn, is p prime of 0 is what's the derivative, or what's the rate of change of the population when time is 0? Well, the formula doesn't take time and plug it in for the derivative. It takes the population. So it's really, you could say something like this in your notes. You can go p prime Well, let's do it this way. dp dt when t is equal to 0, that's p prime of 0. But that's the same thing as dp dt when p is 50. And that's what we're doing. We're plugging in 50. And when you do plug that number in, I got a number of 17.5. And I don't have any units on this, so it's increasing at a rate of 17.5 per unit time. Per year, you could say. Whatever they are. So that's the second answer. And then part C, well, C is saying, when will the population reach 50% of its carrying capacity? Okay, here's the formula. P is equal to 400, was it? Way up there? Or is it way up there? Where are we? Oh, we haven't done it yet. That's right. We need the actual formula. So we have to write P is equal to M over 1 plus M minus P0 over P0 e to the minus kt. Okay. Our problems take a long time, don't they? Parts, all these different parts. We know M, and M is 400. 1 plus 400. We know P. P is 50 they gave us. Over 50 times e to the, we don't know k. Okay, and we're going to have to find k. But this turns out to be, as it turns out, it's equal to 400 divided by 1 plus, it looks like 7 e to the minus kt. Our question was, when will it reach 50% of the carrying capacity? Well, since M is equal to 400, which is full capacity, then 200 is equal to half capacity. So we're going to set this function equal to 200 and solve. It's a good thing this is on video, huh? Boy, this guy's talking fast, kind of. Well, the way I do it is, let's see, how would I do that? I flip it, okay. You can do one of two things. You can flip them over. 1 over 200 is equal to 1 plus 7 e to the minus kt over 400. That leads to 400 over 200, or 2, is equal to 1 plus 7 e to the minus kt. You know, we're off to the races, right? So 1 is equal to 70, and the rest is just basically mechanical. 1/7. Okay, natural log of 1/7. Good so far? I like to do this trick where I go, see that negative? I'm going to bop it out. In fact, I should do it in red. I'm going to bop it out and make it a negative there. But if you make that negative there, this power can come in as a -1 power. It's fun to do. So really you're looking at natural log of 7 is kt. So therefore t, the final answer is take the natural log of 7 and divide it by, what am I doing? Oh, how long does it take? Divide it by k. Did we find k? Oh no. Okay. I'm gonna have to. Oh yeah. I'm not going to quit this video. I forgot that we had K way up here. Where is K? And you're probably yelling at me. K is? What is K? Did we find it? Right there. I forgot about you. So K is actually 0.4. In fact, I didn't really do very well with that demonstration. I should have put K in at the front end and said, by the way, we know K. And I said we didn't. We figured it out. So anyway, the answer to this one is 4. I got about 4.86 years. Sorry about that delay, but this is what you get during, we're doing our first video and going crazy. I'm going to do one more. It's a long one. You can pause if you want. It's a long video. You can do this last one. It's number 12 in the homework. Okay. So a lot of moving parts there, and I've been making videos all morning, so bear with me. It's going to be okay. I hope that makes sense, but if not, we're going to do another one. In this one it says, hopefully this helps, a biologist stocked a lake with 400 fish and estimated the carrying... Okay, wait a minute. He stocked the lake with 400 fish. You know what I do? P0 is equal to 400. I know we're going to start with 400 fish. And he says the max and the carrying capacity for the fish, the max pop is 10,000. So now we know that M is 10,000. I don't know. They estimate it, right? And the number of fish tripled in the first year. Okay, this is enough information for us to feed a logistic. So it's going to grow. So you've got to, you don't need a picture, but up here is 10,000. Sorry. And this is the population, and this is the time. We're starting down here at 400. And what's going to happen is we're thinking it's going to swoop up, but then taper off. That's what we're thinking is going to happen. We have a table, T and P, plug in 0, and we're supposed to be at 400. It said it tripled in the first year, so we're at 1,200 in 1 year. The first question is, it says basically, find the equation, and then the next one says, part B says, how long will it take it to increase to 5,000? So our last question of this video is, can we get the time it takes to get to 5,000? Well, what we want to do is rapidly construct this, and anytime you want to, I invite you to pause and come up with your answer on your own and then see if they agree. Sometimes I'll do that on videos. This one, it was just like, let's show you how to do this, but I'm going to pause and let you do it. I'm going to sit here for 20 minutes. Just kidding. Pause it. All right, you're back. All right. So we would say that P itself is what? 10,000 over 1 plus M, which is 10,000, minus 400, all over 400, e to the minus kt. That's good to know. What we don't know this time, which I forgot in the last problem with a big pause, was k. We do not know this time what k is. We don't know what the differential equation looks like. Anyway, this becomes, with a calculator, 1 plus, I think, 24 e to the minus kt. Okay, so we used that information from the initial condition. We're now going to use this fact that it tripled in 3 years. So when we plug in t is equal to 1, in 1 year, equal 1, then p triples to 1,200. So we end up with, if we plug in 1,200 on one side and 1 for t on the other, we get 10,000. 1 plus 24 e to the minus k times 1. Okay. Flip it over. Maybe if you like that move, it's 1 over 1,200 is equal to 1 plus 24 e to the minus k. See how we're going to figure out k? All over 10,000. So that means 10,000 divided by 1,200. Get that over there. Let's say minus 1 to speed things along is 24 e to the minus k. And no t because t is 1. Okay? So this cancels and cancels as much as you want it to. How about by 4? I got a 25, I think, over 3. But then it's going to be minus 1. So that's really equal to 22 over 3 is 24 e to the minus k. We're finding k right now. Okay, so divide by 24, maybe reduce a little, and we're going to get 11 over 36 is e to the minus k. If you did it, maybe we're following your footsteps. So we get the natural log of 11 over 36 is negative k. So k itself is minus the natural log of 11 over 36, which is the natural log of 36 over 11. So that's actually what k is. That's helpful. What I do is I put that in a calculator and I store it using the store function. And what I got there was like a 1.18 whatever. That's in my calculator. Now I go to the equation knowing what K is. Here's our equation. And I'm going to plug in, it said, how long does it take to get to, remember this chart, half the carrying capacity? So we're going to force T to be something. We're going to make, what is it, P equal 5,000. We're going to plug in 5,000 into this equation. So we have 10, and it's going to be another solved problem, 1 plus 24e to the minus kt. But now we know what K is, right? We know what K is. All right, so flipping it over, 1 over 5,000, we're on our way here, basically. The video is almost over, so 10,000, and unless it shuts down on me, plus, and this is a 24e to the minus kt. I didn't flip it over like I was supposed to. Okay, wasting time. So 1 plus 24 e to the minus kt all over 10,000. If you bring the 10,000 over, you get a 2. Let's subtract the 1. That's equal to 24 e to the minus kt. So 1 over 24 is equal to minus kt. How about we do kt is equal to, oops, okay, ln on this side, ln of 24. I'm going too fast, trying to do this too fast. So you get a 1, you divide by 24, you have to ln to bring that guy down. I think you're following. And then finally you get this equation that says t is equal to the natural log of 24 all over k. Well, k is in storage. When you calculate with a calculator, I got, it looks like 2.68 years roughly for it to reach max capacity. Looking at your table up here, does that fit? 0, 1, 2.68. Yeah, kind of fits. So I think we did pretty well. And that's it for today. I'm going to shut this thing down. Any questions, give me a shout, email me, and I'll help you out. Okay, ta-ta.